Okay, it's time to start. I have several notices listed in this slide. First, reproduction is prohibited. Second, reproducing all or any part of the content is prohibited without the author's permission. And third, this seminar will be recorded and the video will be available on the RIKEN-AIP website later. And fourth, if you have any questions and comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions and comments in the box. So, okay, and today's speaker is Naoya Takeishi from University of Applied Sciences and Arts and Western Switzerland. And the title of this talk is Physics Integrated Variational Autoencoders for Robust and Interpretable Generative Modeling. So please start if you are ready.
Thank you. So again, thank you, Tabe-san, for a kind of introduction and for also giving this opportunity to talk on this AIP seminar. And thank you for Tsumura-san and Hoshino-san for organization. So I am Naoya Takeishi. I am a researcher working at the university known as University of Applied Sciences, Western Switzerland. So this is quite a long name. So this is actually a kind of association of many schools which scatter over mainly the French-speaking region of Switzerland. And I am particularly living in and working in Geneva, which is one of the biggest city in the Switzerland. So the topic of this talk is about what's called gray box or hybrid modeling plus deep generative models. So the idea is to use some prior knowledge, especially domain knowledge, expert knowledge about the target programs, as well as some deep neural architectures for generative modeling. So the generative modeling for, of course, for density estimation or something like that, and for generating new signals from that learned model. And this is a joint work with my boss, Dr. Alexander Karosis of the same university. Then let me start with some motivation presentation. So as I said, motivation is gray box modeling or hybrid modeling. And actually the word gray box modeling, this is, I think, traditionally what has been used in the area of automatic control, not really in machine learning. But I slightly abuse the word usage here, so differently from the semantics in the automatic control literature. So I here, by saying gray box modeling, refer to very general combination of theory or knowledge in each domain and data-driven models, which also, of course, include the deep neural networks. And here, theory of knowledge will come from various areas such as physics in a narrow sense, physics, or chemistry, or biology, or even economics, engineering, or some more various disciplines of science. And the data-driven model will come from also it's anything. Any models in which may be used in machine learning. And why this kind of gray box modeling or knowledge infusion is important is, I think there are multiple reasons, but it includes, for example, the learning may become efficient by integrating some knowledge. I mean, in terms of sample complexity, hopefully it may become more efficient, or more importantly, by inducing some knowledge, the part of the data-driven model, which is usually not very interpretable, will hopefully become somewhat interpretable. So the part of the model will become interpretable, which is a clear advantage in application, and vice versa, and also many things. And the question here is that, can we do it? Can we do the gray box modeling for deep generative models? This, I think, is not really obvious. And before jumping into this particular topic, I would like to present some broader picture about the knowledge incorporation into machine learning. So as you know, machine learning never holds without some knowledge, which is often called inductive bias in the literature. And so you see here very typical procedure of machine learning, solving machine learning. First, you set some program in terms of, for example, regularized risk minimization. So to minimize some loss function on data set D, loss function plus regularizer. You minimize. So you feed the hypothesis which minimize this objective. So this is problem setting, and in the training phase, you actually solve it. For example, in deep neural networks, you often use a stochastic gradient descent. You set the initial value and do updates. And afterward, you do test, which is a kind of inference or prediction on new data using the learned model. So this is a typical procedure of machine learning. And within these procedures, there were everywhere the knowledge comes in. For example, the hypothesis space, the model can be crafted based on some prior knowledge, domain knowledge, and which is actually what I do in this talk. And also the loss function or regularizer or even data can come from knowledge-based something, model or something. And another perspective is, for example, the initialization can be done with some domain knowledge or some domain-based data. And also even after learning, the learned model may want to be verified against some domain knowledge. So as you see, there are knowledge incorporation everywhere in machine learning. And also, though I didn't draw it in this slide, there were other regions where knowledge come in, like of course reinforcement learning. There comes in a simulator, or what's called a likelihood-free inference or simulation-based inference. It's a Bayesian inference based on the simulation, which is a particular domain knowledge in each application area. But in this talk, I will focus on the first point of view, which is crafting hypothesis space or crafting model based on some domain knowledge. And I hear one further note is that I here refer to, by saying knowledge, I here refer to very domain-specific knowledge rather than general knowledge like smoothness of function or sparsity, which is often referred to as inductive bias. But differently from that, I here refer to more domain-specific things. So this is kind of background and introduction. And let's start the particular topic of this of our particular study. So the target of our study is to do a gray box version of deep generative modeling. And I particularly focus on the deep generative modeling of type VAE, a variational autoencoder, where there were two neural networks components, basically. So there is data X, and the data is input to what's called encoder or recognition network, which computes the latent variable or sufficient statistics of the latent variable. And this latent variable is then put into the decoder, which is the data generating process, and finally generate the reconstruction of the data. And this is learned by maximizing the lower bound of the marginal likelihood of the data, which is equivalent to the minimization of the reconstruction loss between two, and some regularization on the latent variable. So I think many of you are familiar with this autoencoding, and particularly variational autoencoding architecture. So this is the base model. And what I want to do is to make a gray box version of it. So gray box version should be somewhat a combination of the neural network-based autoencoding architecture and also some physics model. So what I call physics model is a model which comes from some knowledge or theory of each application domain. And I here just for utility, just for simplicity, I here call it the physics model, though it's not really physics, maybe it may be biology, it may be chemistry, economics. So, but I use the word physics here in a very broad sense. So it's a very broad notion. So the model, the overall model of the target gray box modeling is like this. So there are two parts in the decoder side, of course. One is a physics model, what I call physics model. And also there comes some neural network model. So why this combination is needed is the point maybe. And the reason for this combination is that we assume that this physics model, this knowledge-based model is not perfect. So it is not perfect, but possibly and plausibly misses some important aspects of the true data generating process. And then we need some kind of data-driven model here, neural network, to complete the missing part of the physics model. So this is why we need gray box modeling, why we need to augment this physics model by a neural network. So this is the decoder part. It's twofold. And of course, accordingly, there were two types of latent variable. The top one is the same with the usual VAE, which is usually a Gaussian latent variable. And this one, so this one is for the physics model. It's typically some of the parameters of the physics model. So this is also latent variable. And accordingly, of course, there are two encoder, and now these are both neural networks. So this is the overall picture of the what I call physics integrated VAEs, which is, I think, instance of the gray box deep generative model. Yes, so this is the model. But what the research question is that in some pathological learning case, it is possible that the physics model, the knowledge-based model part, is somewhat ignored by the overall model because the neural network is very flexible. You know, it has it can approximate any function. So it is always possible that this neural network just learns everything, and eventually physics model is not used at all. So, but this is not what we want. This is not what we want, but we want this physics model to work to a reasonable extent. So we have to avoid this phenomenon. By the way, I'm happy to answer any questions in the middle, so please write any question in the Q&A. So this is the central research questions. And I will present some ideas to resolve this issue. First one, so I will present two regularization. This is first one. In this regularization idea, so I want to somehow suppress or somehow limit the flexibility of the trainable part. But it must be done carefully. For example, the obvious way is to use very simple and very low dimensional latent variable and very simple neural network here, like even linear model, but it's not what we want. It's not the advantage of neural network. So neural network should be flexible, but at the same time, it should somehow be suppressed to not to ignore the physics model. So this is a dilemma, I think. And the idea, the particular formulation of this regularization, which I present now, is to minimize some statistical distance d. It can be anything. Statistical distance b between two models, particularly between two posterior predictive distributions of one is the regional model, which we will learn, as usual, using a stochastic gradient descent, and some physics-only version of that model. So we call it physics-only reduced model, in which the neural network here, while it's replaced by some simple function, some trivial reference baseline function, which I call baseline function H. And then putting aside how this can be, how this should be done. So this model is, so there in the decoder side, in this model, there is only a physics model which generates the data, and this H is just helping it for example, aligning the dimensionality of the data. So this is kind of physics only model. And this H can, it depends on the original formulation of this combination, but typically it can be some sorry, this should be H of Z, not H of X. So this should be H of Z. Typically, it's just the identity function. It's just a zero valued function, or maybe in some cases it's a linear function. So I replace neural network by this H and minimize these two in order to suppress the flexibility. So unnecessary flexibility of this neural network. So this is the idea. And for this statistical distance, I just used the Kerr divergence for simplicity here, but it can be anything like other F divergences or corner-based metrics. And so one side effect of this kind of minimization is that these two latent variables tend to be independent each other by this minimization. So this is not written explicitly, but it's a side effect of this minimization. And I think it's intuitively a good thing, because these two things should be assigned to different things. And then these two latent variables should be independent as possible. So this is the first regularization idea. And actually, there is another thing, because I think the first one is not necessarily sufficient for perfectly grounding the semantics of this physics latent variable to what we intended, that is the physics, the parameter of the physics model. So it may happen occasionally, but it's not necessarily happen. Because of the still the flexibility of this part, this neural network part. So I think, I mean, it's still possible that this becomes something like a constant value, and this physics model, okay, it's not be ignored, but it's meaningless. This is still possible. So the idea of this second regularization is to prevent such kind of phenomenon. And for that, the idea is to use this incomplete physics model for data augmentation. Since this physics model is, okay, it's incomplete, we assume that, but it still contains, we believe, it still contains somewhat useful structure which capture the true data generating process. And thus, we can generate some signals by, for example, randomly generating the latent variable here, and just replacing the neural network here by the simple function, such as zero or identity, and use this for generate new data. And then put this new data to the original model, and this physics part encoder infers the latent variable, so we can supervise it by what we generated, the ground truth. So this is, I think, data augmentation. But the problem, so this is the idea, what I said, put the generated data to the model and supervise the inferred latent variable. But I think there is a problem here, because this incomplete physics model will generate something very different from the real data, because this is incomplete. But the real data is from some, I mean, real signal, real process. It's it's complete by definition. So these two things, the extra new data and the original X, these have different natures. So we cannot really put this directly to the model. So the idea is to make this physics encoder have some special structure. Here I will make it somewhat two-stage structure, which I will explain. So this is an overall view. Here, the physics encoder GPhys is decomposed into two stages. I think it's without loss of generality. So it's now two stage. In the first stage, so the point is the functionality of this first stage. The first stage of this encoder, GPhys1, should transform the original data into something. And this something should be similar to what would be generated from the physics-only model. Does it convey the point? So again, this X is first put into GPhys1, which is the first stage of the encoder. And this first stage of the encoder should somehow kind of cleanse, transform the data into kind of physics-only version. So it should drop the non-physics. It's not non-physics, but the component which is not considered in the physics model. It should drop such component and output something. And if such a functionality of this first stage is ensured, putting aside how to do it, if such a functionality is ensured, then we can input the newly generated augmented signal to here. It's an output of GPhys1, or it's equivalent to the input of GPhys2, the second stage. And then GPhys2, the second stage, it as usual infers the physics part latent variable, and then we can supervise it. By this process, we will hopefully ground the semantics of this latent variable. Okay, but obvious question here is that how to do it, how to ensure the functionality of such a first stage of the encoder. I think, yeah. And also, okay, let me explain the idea, which is actually rather heuristic. I don't think this is a sufficient strategy, but empirically we confirmed that this heuristic strategy works. So it is like this. First, let's start from the beginning. So first, here the real data comes, X, and it's put it to the physics part encoder. And at the final, at the first stage, as I said, it outputs something. And then the second stage receives it, then finally outputs the inferred latent variable. So the idea is to put this inferred latent variable, physics latent variable, to the, again, the physics-only model where the neural network was disabled. Put this to physics-only model and obtain some physics-only version corresponds to the value of the phys currently. And this physics-only version should actually be similar to this one, given the desired functionality of the first stage of the encoder. So the first stage of the encoder, I said that it should output some version of the original data, which is a physics-only version of the original data. And here is the physics-only version we want. So the idea is just supervise this intermediate variable with the physics-only signal, which is generated from this latent variable. And I think you see this is somewhat tautological. It would not work in the worst case. Yes, it would not work. I don't think it is. So as I said, it is a sufficient condition to ensure the functionality. But empirically, it works to some extent. So by this mechanism, we make this output of first stitch similar to physics-only version, and then we can supervise it. I mean, we can supervise the latent variable of physics part by putting the newly generated signal to here. So sorry for this confusing idea, but this is a second regularization idea. Okay, since there have been no questions yet, so I will keep on if you have no questions.
I have some question.
Yeah.
I missed something. So if we use some original model, it resulted in overfitting or something.
Yes. So you mean in this slide or in the previous one?
Yeah, previous one.
This?
Yes.
Overfitting of the original model or the
Overfitting? Original model have the results of overfitting?
Yes, I think so.
Okay. So that's why you, yeah.
Yes.
Yeah,
I think
we need regularization.
Yes, I think so, because the ignored physics phenomenon is, I think it's a particular instance of the overfitting, where the overfitting is done in the way that the neural network does everything, and just the lower part is ignored. I think it's one of the instance of overfitting. And yes, that kind of overfitting should be somehow particularly prevented by some regularization. The idea is what is presented here. So yeah, thank you.
Thank you. Some audience has some questions, so please.
May I ask a question?
Yeah, of course.
Would you just show me some example of the variable G physics and G physics and F physics? Is there any simple, concrete example?
Yes, exactly. Yeah, thank you for the question. I will present some experiments where some concrete examples will come. Okay. So one simple yet artificial example is, for example, the pendulum. We have many data of the pendulum angle time sequences, and of course the data will come from the perfect pendulum equation. But for example, we may know only the part of this pendulum equation, like only the first term. So yeah, I know this is artificial, but this is an example.
I see. Is your method different from the one in which the data is generated from the physics model, and then combine this simulated data with the real data, and then apply, for example, deep learning or something?
Yeah, I think that is really a good point, because I think such an approach will correspond to what I presented here, the data from knowledge-based model. It's also frequently done. It's a frequent approach in order to combine some domain knowledge into machine learning. And I would also say that this second regularization is somewhat similar to that, because here new data is generated from physics model and then used along with the original data. So I think it's a kind of an instance of that approach.
I see. Thank you very much.
Thank you.
Takeishi-san, could you read Q&A?
Yes. I think from the older one. So okay, thank you for questions. So the first question is, I want my trained regressive models trained on real data, not synthetic, to be able to extrapolate a little, but I don't have an underlying physics-based model at hand. So which ML method would you recommend in that case? So, okay, thank you. But this, I would say this is a difficult question because I think the most correct answer is that it depends. It depends on the application, of course. Why it depends is that for extrapolation, I think, without any very difficult notions of mathematics, signal processing, everything, for extrapolation, I think that kind of knowledge, kind of physics model, what I call, is very necessary, without which we have almost no hope for extrapolation. I mean, we should never give up that we don't have much hope for extrapolation. And if the physics model is missing, maybe the machine learning model, I mean, for example, neural network part can be created with some very modular knowledge. For example, as you know, the one most famous example is that I think convolutional neural network, which is very good at images or other translation equivariant things, which is because the CNN is indeed a translation equivariant. So I think if the concrete, for example, mathematical equation of physics model, even if that kind of thing is not available, we can still look for some modular, more small sized, I don't know if it is small or not, it is small or big, but more abstract kinds of knowledge correspond to the problem. So I think this is not a clear question, a clear answer to that question, but this is my answer so far. So, okay, maybe what I will show afterward is only experiment. Maybe I will go on the questions still. So the second question is, isn't X the input to the physical system for identification? Well, I'm not sure what the physical system is meant for, but in a sense, in my understanding, this data X is exactly for, in a sense, identification, because we want to know the forward model, the forward data generating process, and we want to learn, or in other words, identify that process. So I think this is almost the same with what's done in the system identification, particularly in a control theory. And I'm not really sure what the differences are, but yeah, to the question, yes, this is X is for the identification. But we don't, what's particularly different from automatic control system identification is that we don't really specify what X should be. For example, in my understanding, in automatic control system identification, the data should be, it depends, but in typical case, data should be something that is generated by known input. I mean, known input signal, such as impulse, impulse input, but or some other types of excitations that have particular property. But here, differently from that, X is not really assumed to be some kind of excitation. It can be anything, any measurement, basically. But yeah, yes, this is my answer. And the third question is that can a stochastic physics model, for example, Langevin equation, fit into this framework? Yes, this is a very good point. So this physics model sorry, you don't see anything. So this physics model part can indeed be some stochastic differential equation, for example. And in that case, that random, so you know, there is a random variable in this stochastic equation, and the realization of that randomness, for example, the process noise, should come in this latent variable. So it is theoretically possible by this kind of treatment where the stochasticity is in this latent variable. But I think in practice, it is not that easy, because if for example, if all the stochastic, all the randomness of SDE comes in this physics latent variable, and then physics latent variable becomes very high dimensional, and then the inference by encoder network is okay. It's maybe not impossible, but it will be very challenging. So in that case, in that sense, it's possible, but will be challenging. So thank you so much for the questions. And if there is no question for now, I will proceed to the experiment part, which is not really long. Okay. So yes, the experiments, I conducted several experiments with some instances of deep generative model. And this first instance is what I showed slightly. Is an example. This is particularly an artificial example where the data is a correction of time series, and each time series is a measurement of the pendulum, which is oscillating, just oscillating angle, the angle of just a single pendulum. And the pendulum's equation motion is presented here. This theta, var theta, is the angle of the pendulum, and this second term is just for its oscillation term, and the third term is some damping effect due to something, I don't know, air resistance, something, and the final term is some external force applied to the pendulum. So this is kind of complete equation of pendulum, and the data is indeed generated from it, where in each sequence the value of A and B and this phi are randomly drawn. So this is data, and the what we want to do is to learn a generative model on such data, where the encoder, so the generative model is VAE as we talked, where the encoder is neural net as usual, and the point is in the decoder. So the decoder is combination of some physics model and some neural networks, where it's not simple combination, but rather there is a solver, ODE solver, solver of the ordinary differential equation, this, which should be differentiable also. And this equation, F plus Fnn equals 0, this differential equation is solved by this solver, and then further transformed by another neural network. So, and this another neural network may not be necessary, but I just used it for experiment. And the point is that this F-phys, the physics model, is not same as this. It's just these first two terms of the true data generating process. So this is a physics model I gave, and thus this physics model is obviously incomplete. It misses these terms. So the hope is that the effect of these terms are learned by this neural network and possibly by this neural network. So what you see in the bottom is some output from the learned model. The proposed model with the proposed regularizer is with this red line. while the ground truth is this thick black line. So this is just a particular one test sample. So there are many other samples, but I'm showing the one test sample for just for simplicity. And what you see is that, so I forgot to say that the training data, this training data is generated from only limited time range, which is from time 0 to time 2.5. The training data spans only this time range. So only this part of the figure is ground truth and reconstruction. And this proposed method and this green dotted line, and then plus solver, what it says, it corresponds to the case where this physics model is not there. Without this physics model and slightly increased, slightly bigger neural network, we solve ODE. So it's a pure neural ODE, and then transform it. So this case, that case is in green. So the reconstruction is good for both methods, but in an extrapolative region where the time is more than 2.5. So it is not pure reconstruction because training data is up to time 2.5. And if you see this, the red line, the physics augmented one plus proper regularization, it successfully matches the truth, whereas the non-physics neural network only model, okay, it may be okay at the first, but it rapidly deviates from the truth. So I think this is what typically happens in the extrapolation without any particular knowledge. So this is a kind of artificial experiment. And I show next is more realistic, but I admit it's still artificial, but more realistic example. Here the data is a collection of images of certain kinds of galaxy. And the goal is to learn a generative model on such galaxy images and generate new galaxy images. So I don't say this is useful, but I think it's a nice proof of concept experiment. So here the model, the encoder is just a CNN, so UNet like CNN with skip connections. And the decoder is again it's a combination of physics model. And then the output of physics model is transformed by some neural network. So this is simpler. Sorry, encoder is not UNet. Decoder, neural net is UNet. And decoder neural net is UNet, which is a special type of CNN. And decoder physics model, this is chosen from what is often used in astronomy. Astronomers often use, for example, Gaussian profile of certain type of galaxy light intensity, and I just followed that tradition, which has 4 parameters. 4 of 2 are semi-major axis and semi-minor axis of the ellipse. I mean, it's a Gaussian, so it shows some elliptic like level set. So the parameter of this model is semi-major minor axis of that ellipse, and the tilt of that ellipse, that third parameter. And the final parameter is the intensity, particularly the central point intensity of light. So these 4 parameters determines the Gaussian profile light intensity of galaxy of certain type. And I use this as a physics model. Here, what you see is that the top left is some example from data, test data, where each is a galaxy. I don't know what it is, but it's a galaxy. And the remaining ones are some random generation from the learned model. So the bottom right is generation from the deep box model. where the regularization is properly done. So it's, I think, quite similar to the data. And since this physics model is, it's morphologically okay, it generates this Gaussian like light intensity. But what's particularly missed in this physics model is the color. It doesn't consider the color difference between each color channel. So it must be learned by neural network. And if you look at the random generation results from the learned model, you see that some are close to red, some are close to blue. So it's properly learned, the color differences. And for comparison, you see the bottom left, you see it's still this model. It's still a combination of physics and neural network, but learned without the proposed regularizer. In that case, some sample seems not bad, but many others are still not good working. So this is, I think, this shows the effects of the regularization. And just for information, the top left, top right is generation from neural network only model, which is not good at all. So this is not good at all because I used the training data as training data. I used only 400 images. I think which is exceptionally smaller compared to the image generation models in a typical examples. And that's why neural network only model was not very well learned. So yes, I only show the 2 experiments, but the paper has 2 more experiments. So if you're interested, please see the paper. So the summary is that I presented the idea of gray box modeling with neural networks, particularly for deep generative models. And the take-home message here is that you should be careful. You should not do this gray box modeling very naively, but you should be careful so that the physics model is not ignored by the flexibility of this neural network. And obviously, there are other challenges like dealing with very complex physics models like fluid simulator, or possibly misspecified physics models. Also, for example, in the case where we are not really sure that the given physics model is perfectly okay, so we have to be careful about that, the possible misspecification. And also, we are intensively working on applications. For example, I'm particularly working on the gate human locomotion generation using differentiable physics engine. And the final note is that this work will be presented in the NeurIPS this year. So I'm happy to discuss also in that occasion. So this is the end of my talk. So thank you so much.
Thank you, Takeishi-san. And some audience has question. Could you see?
Yes.
Q&A?
Yes. So maybe I will proceed with the questions. So the first one is, won't you consider ML methods other than deep learning ones? Some very interesting data sets are not big data. Yes. Yes, thank you. And this is, I think, this very good point. The answer is, in short, I'm not really sure about the use of non-neural net models in, you don't see anything in here. So I assumed here neural network because it's very flexible. And then the potential problems of ignored physics comes. But if this machine learning model is not neural net and it has only less flexibility, then I would say that case would fall in the more traditional program setting where, I mean, traditional gray box modeling, where basically we don't really be careful about the ignored physics phenomenon, and we just learn, and we just compile the model and we just run it. So I think if here is not neural network, especially deep neural network, I think that learning problem be much easier. In that sense, I didn't consider it. But yes, but some very interesting data sets are not big data. I totally agree. Sorry for vague answer, but it depends, depending on the size of a particular data set, the effort for designing the model carefully will still remain forever. So yeah, sorry for vague answer, but this is my answer for that question.
Thanks. So, any question, comments? No. Okay. Now I have a question. And in your paper, you mentioned the work of IN. They also presented a physics integrated model.
Yeah.
Can you give a comment on their work, especially for difference between your work and IN?
Yes. So thank you for pointing out that point. It's very important point in terms of related work. So their work, so it is a work in the clear this year, I believe, the augmenting physics model to, sorry, I forgot the title, but there the combination of physics model and neural network model was restricted to be additive. So it's F physics plus F neural network. That's the particular architecture they considered. And they regularized the functional norm of this neural network to prevent the ignored physics phenomena. So in a sense, their work is included as a special case in this very general formulation. So yes, that's the connection.
Thank you very much. And the audience has some questions.
Yes. So are there any methods to visualize the learning weights or tensor? I think so, yes, but I'm not sure which methods are particularly popular nowadays, but I think you can always see the particular realization of the learned weights and see what happens inside. And I think usually the interest is in visualizing the first, visualizing the last layer, what's happening in the last layer. For example, if you look at the last layer's contribution by looking at the weight absolute values, you may find out that how much physics model is used, how much neural network is used. But the one point here is that it depends on the architecture. For example, in the IN's work, as Takeishi mentioned, there the combination of two models are additive. In that case, maybe you can see some coefficient in that addition to see the exact contribution ratio of two models. But otherwise, in general, if you can visualize the weights, I would say it's not very easy to understand what is happening, even if you can visualize. So visualizing and understanding are obviously different things. And my point is that for understanding, we are not very good yet. And the next question is that, can you extract new physics from your model extrapolation and give feedbacks to the model? So thank you for this question. I think this is very important and very have been questioned for decades, even for centuries. Because here, so for example, I mean, the point of this particular work is not to extract new physics, not to find new physics. We want to use the existing knowledge of physics and let neural network do anything else. And that's all, we are happy. But in more advanced setting, I agree that finding new physics is very demanding task, but and that is very difficult and different from what I did in this work. But still, if I comment something, for example, after learning this neural network here, you may do something like knowledge distillation to find out some modular symbolic structure inside it. And then that found modular symbolic structure, move it into physics model side, and then again put new neural network and learn it, find something, put it here. So such kind of iterative process would be, I would say, it's theoretically possible, but yeah, but I didn't try anything like that. But yes, I think it is very interesting, challenging future direction.
Thank you. Any question or comments? That's it. Okay. I will close this session. So thank you for attending this.
Thank you so much.
Yeah.